Okay, folks, welcome to the final session. In this one, we'll have two short talks from ETH. And the first speaker is Marco Eilers. And so Marco just got his PhD. So congratulations from Peter's group.
Thank you.
And Marco worked on Viper and also did work on deductive verification. In particular, I think built some tools, verifies for Python programs. Mm-hmm. Right? And so Marco, after his PhD, he's currently still as a postdoc in Peter's group. Yeah? So good. Yeah, Marco.
Thanks a lot for the introduction. My name's Marco, and this talk is going to be about COMCSL, which is a new program logic for verifying information flow security for concurrent programs using abstract commutativity. And this is joint work with Thibault, who's sitting somewhere over there, and with Peter. So the topic of the talk is information flow security, and a popular, or maybe the most popular way of formalizing this is as non-interference. So the idea is we have a program that has as inputs some set of secret variables, secret inputs that are also called high sensitivity or just high, and I'll call this H throughout. And we have some low sensitivity inputs, so those are public. Those are the ones we can leak. And now what we want to prove is that our program doesn't leak any information about the high inputs through its public output. So if you want to look at this more formally, you can phrase it like this. Whenever you have, for any given execution of your program that you have with some low input L and some high input H1, if you run it and get some result, then if you run it again with the same low input but a different high input, then you want to get the same result. So that means changes in the high and the secret inputs aren't visible in the output. This is what we want. And so for this example program here, that's obviously not the case. If we run it with the high input being 0, we get 2. If we run it with the high input being 3, we get 1. So this is a case that we would want to reject. And reasoning about this, verifying this for a sequential program like this, this is, I don't want to say a solved problem, but in principle, we know how to do this. So there are type systems for this, there are programming logics, all this kind of stuff. It's still obviously not easy to do, to scale it up and automate it and be precise, but it's clear how to do it in principle. Now contrast that with side channels, in particular for timing. So we've already heard something about this. So again, some example program, if H is greater than 0 here, then the program just performs a bunch more computation. So clearly, depending on the high input, it'll run for a longer time or for a shorter time. So if you have an attacker that can observe the runtime, they can conclude something about the value of H. And unlike for values, reasoning about timing can be really, really, really complex. So first, we have the problem that usually the high-level language program that we're seeing here is not going to be the one that's directly executed, right? This will run through some compiler that will run some optimizations, and then some assembly language program will actually run. And then we have the problem that it's going to run on some processor, which may have instructions that whose runtime is data dependent, for example. It's going to have caches. It's going to do speculative execution. It'll have a branch predictor. All these things can influence execution time. So it's just really, really, really difficult in general to look at a high-level program like that and conclude this definitely doesn't leak any secret information via timing. Okay. So we have this contrast here. Reasoning about values, comparatively simple. Reasoning about timing, comparatively difficult. And the nice thing is that we can basically regard this as almost completely independent problems. Sorry. So there are going to be cases where I have an attacker that can observe the output of my program and the timing, and then I'm going to use techniques that assure me that it doesn't leak through the output or through the timing. There are going to be cases where the attacker can observe only the timing, actually, or only the value. And these scenarios are quite common. So, for example, cases where I care only about the output value will be ones where the timing is hidden, for example, behind a very laggy network, or if I execute my program as a part of a batch job overnight and then, publish the results at 10 in the morning or something. At this point, an attacker has no way of observing how long the program execution actually took, right? So these problems are basically independent, and if I only care about values, I only have to solve a simple problem, which is a good thing. until my program becomes concurrent and I have shared memory concurrency, and that ruins everything. So here's an example. The two lines here are parallel execution. So I have a left thread and a right thread. The right thread just counts up to 100 and then sets a shared variable to 7. The left thread counts up to the secret value h and then sets a shared variable to 6. Now, both of the threads individually don't do anything wrong, right? They don't assign any information about the value h directly to the shared variable. But now, if you run this program, because these assignments are essentially racing with each other, you get the following situation. If you run it with a low high input, so for example 4, then the loop on the left will terminate much earlier, and its assignment to shared will happen earlier. So this assignment essentially will win out and overwrite the previous one, and you'll see value 7. If you have a very high value for h, then the other write will win out, basically, and you'll see 6. Yeah?
Are you making an assumption on scheduling?
What exactly you're getting here depends on scheduling, obviously. So if you have a round-robin scheduler, then you can, in this case, say this with certainty. Maybe you have a probabilistic one, then you'll learn something like this probabilistically. But basically, in each case, you can leak some information, either be it probabilistic or deterministic in this way. And obviously, this is also a very artificial example for purpose of keeping it short. But you can easily build examples like that are real and that are problematic in real life. Okay. So the message here, the problem that we're facing, is that if I have a timing channel, an internal timing channel, and I have shared memory concurrency, then together these can transform the timing channel into a value channel. Right? The timing difference that I saw here, the secret dependent runtime of this loop, is what ultimately caused this leak into the variable shared. So that's the problem. Now this problem this has been known for a long time, and there are solutions for this problem. So there are static analyses, there are type systems, there are program logics that all attack this problem. And they all do it in more or less the same way. So they see the problem that we have secret-dependent timing that influences the order of modifications of shared data, which then influences the final result value. And their solution is basically, okay, then let's get rid of secret-dependent timing. And that works in principle, right? That we stop the chain here, no more leaks. The problem is that, as I've already said, preventing secret-dependent timing, runtime in general, is really, really, really difficult. So what these techniques then generally do is that they assume a kind of idealized execution model, idealized hardware, where, for example, it is sufficient to just say we forbid branching on high values, and this is the only possible source of secret-dependent timing, and then this is sufficient. And that works in these idealized scenarios. But then if I run the program on like my laptop or your laptop or my phone or whatever, this is probably not enough. So that's a problem. So the way they would reject this program here would be to say, hey, the runtime of this loop depends on secret value h. We can't have that. So for this program, it works. For others, maybe not. There's also another potential problem, which is that these existing solutions are sometimes incomplete. So this is a variation of this example, where we first initialize a shared variable with the low input L. So that's one we're allowed to leak. And I've changed these assignments here so they no longer just assign 6 and 7, but now instead they atomically add 6 and 7. So now if you run this program, it'll always return L plus 13, right? So there's no secret information in here. But we still have a loop whose runtime depends on a secret input. So existing techniques would still say, no, you can't do this, even though it's fine. So the goal that we're trying to solve is to basically make reasoning about values in a concurrent context simple again. We want to be able to reason about values in these concurrent programs without having to reason about timing in any way whatsoever. That's our goal. And so for the rest of the talk, I'm going to try to solve this problem. So I'm going to assume from now on that our attacker cannot see timing, cannot see intermediate results, can only see the final output of the program, right? Because this is the specific scenario that we're looking at. Okay. Now this is the program that I just showed you. And here there's something interesting happening, right? Because we have this timing difference, but it doesn't really reflect, it's not reflected in the output of the program. And the reason is that the concurrent modifications that we're performing here are both additions. So we're adding 6 and we're adding 7. And turns out it doesn't matter if you add 6 first and then 7 or vice versa, because additions commute. So what's happening here is that we still have secret-dependent timing, but the order of modifications of the shared data no longer influences the final result value because these orders commute. And this is the key idea, really, of what we're doing here. We're trying to verify these concurrent programs not by showing that there's no time, that there are no timing differences, but by showing that the potentially different order resulting from these differences doesn't influence the final result that we're returning because these modifications all commute. Okay. So if you have one takeaway, this is the takeaway. That's what we want to do. And so for the rest of the talk, basically, I'm going to try to give you a high-level view of how we build a verification technique based on this idea. Right, and I start with a more basic solution, and then later I'll show you how we can extend this to make it more complete, more precise, and more generally applicable. Right, so what I'm showing here is these are supposed to be 2 traces of a program, of the same program, that has a part with concurrently executing threads. So the dotted lines here are sequential execution. So we assume our program starts with some sequential main method or something like that, then spawns a bunch of threads. They all execute concurrently and modify some shared data. And we join the threads again and return something. And now let's assume that the thing we're returning is the shared data that our threads operate on, right? So we want to prove that at the end of this whole process, the shared data is low. It doesn't contain any high information. So obviously, well, I should say this. It's not obvious. The idea is that these are 2 executions that differ only in their high inputs again, right? So any differences are directly caused by secret data. So if the goal is to show that the final data here, this is the final value of the shared data, that these are equivalent, then we can achieve this as follows. We start out by showing that the initial value of the shared data is low. So that what our threads work on when they first start working, that's a low value. There's not a really secret information in there. Now, these we'll have concurrent threads, and they'll modify the shared data in some way. And now the next thing we'll prove is that secret information does not influence which operations we perform on the shared data. So if we perform some change A, B, C here, this could be add 3, add 5, add 8. Then in another execution with different secret inputs, we'll perform the same changes, potentially in a different order, because the order can be influenced by secret data, but the things we're doing are the same ones. And then finally, we check that these updates commute. Right? And under these assumptions, we're starting out with the same value, we're performing the same changes, and these changes commute. The only difference is the order. So but the difference in the order isn't reflected because of the commuting changes. Then we can assume at the end, or it's sound to assume at the end, that our final values will be the same. Yeah. Okay. So in our verification technique, basically what we have to show is, first of all, that we do actually start with the same shared value initially. Yeah, that's an example, sorry. So we start with 0, we add 1, 5, and 3, we'll get 9 even if we add 1, 5, and 3 in a different order, right? That's the idea. So one thing we have to prevent is that we can get traces like this, right? That here we have 2 modifications of type B, whatever they may be, whereas here we have only 1. So the secret must not influence what changes we perform. This is something we would have to reject. Second, as I've already said, we must make sure that the changes we do perform all commute. So if we have concurrent additions and multiplications here, that's a bad thing because they don't commute with each other, right? The results here will not be equal. So we also have to reject this. Right. So these are basically the properties we have to enforce. And to do this, we've built a concurrent separation logic. And so now I'll give you a brief overview of what actually, well, how you use our logic to reason about these programs. So concurrent separation logic in general is a way of locally and modularly reasoning about, well, concurrent and heap manipulating programs. So the basic idea is that each part of the memory, in particular of the heap, at any given moment in time, belongs to a specific thread. And each thread only works on the memory that belongs to it, and there's no overlap between the memory that different threads work on. What that gives you is the ability to reason about each thread as if no other threads exists, right? Because they can't interfere. We prove that they don't interfere with our own footprint. Now, obviously, you want to have situations where you have shared data, and in concurrent separation logic, the way you achieve this is by explicitly declaring a shared resource. So what we would say here is, at the point or before we start concurrently executing threads, we would say, from now on, we want to treat our shared variable here as a shared resource, which then means that different threads can operate on it concurrently. So when you're proving anything about this program here in a concurrent separation logic, there's this step in the proof where you have to now explicitly say, now I'm sharing this resource for concurrent modification. And we can basically hijack this step and some other steps and add our additional proof obligations that we need for our information flow reasoning. So it turns out the point in the proof where we share the resource is exactly the point where we would additionally want to prove, hey, our initial value here of the shared resource is low. Right? That's a proof obligation that I mentioned earlier, and here's where we can check it. Now, additionally, concurrent separation logic also enforces that on this shared resource, not every thread can just modify it any way it wants to, but instead it can only do so in specific places. So in particular, there are these atomic blocks, or generally it could be a place where I've acquired a lock, but there are only specific places where a thread may access and interact with the shared resource. So in particular, since for us it's very, very important to figure out what are the concurrent modifications, right? So in a concurrent separation logic context, the only places we need to look at are these atomic blocks. So we can look at those in each thread and figure out, okay, these are the changes that it's making. And then finally, if we've done that, there's going to be kind of like an opposite step of the share where we say, okay, now we're done with concurrently modifying our shared data. We unshare it. And this would then be the place where we would want to know that the value of the shared data is low again. Okay, so similar program as before, and I'll briefly show you how to actually do a proof. So any kind of proof like this would usually look like this. You would assume that your low input L is initially low, so the data in there is actually non-secret, and you don't assume this about your input H. So you just assume nothing over it, which implies that it may be high, it may be secret. And your goal is to show at the end the result that I return is low. Right, like obviously to show, since the thing that we're returning is that the value of shared is low, this is what we really need to prove here. And we know, since we assign L to shared, that it'll be low in the beginning. Now we perform the share. We give different threads the ability to access the variable shared concurrently. At this point, we can check that its initial value is low. That's good. Step one done. And at this point now, we also decide which operations different threads may perform on the shared variable, on the shared value. So at this point, we would decide all the threads are allowed to do on the shared value is add values. They're not allowed to multiply. They're not allowed to divide. All they can do is add. And now we can check at this point here in a modular way that, well, all the operations they are allowed to do commute with each other, right? Addition commutes with itself, and we can check this at one specific point. We represent this ability to add things to the shared variable with what we call a guard. So it's kind of in just a separation logic resource that you can have and pass around, basically. So in this case, there would be one guard that would allow threads to add things to the shared value. And we can split this guard up and give a part of it to each concurrently running thread. Right, so that now means this thread is allowed to add things, this one is also. And now for each atomic block that we encounter, what we have to prove is that we have a guard that allows us to modify the shared value in the first place, and that the thing that we're doing, the modification, for in this case we add something, is the one actually allowed by the guard. So in this case, right, that's fine. We're adding something. We have a guard that enables us to do exactly that. And then finally, we also record in the guard the value that we've added. And we do this separately for every thread. So on the left, we record that we've added 6. On the right, we record that we've added 7. Right, then finally, the concurrent modifications are done. We can join the threads, and we can get our guards back together and merge them basically again. And now the point is that we have, this guard contains a complete list, or no, not list, really multiset of the operations that have been performed. So we don't really know about the order, right? We don't know at this point if the 6 has been added earlier or the 7, but it doesn't matter. We know that 7 has been added and 6 has been added, and that these updates commute. So at this point, if we are able to prove that the changes we've made don't depend on secret data, then we know that we're in the scenario that we want. The only thing that is secret dependent was the order of updates, which doesn't matter because of commutativity. So we know we can assume that our shared variable is low at this point. So this is roughly what a proof looks like. And this is basically our first version of the logic is done here. But it turns out we can do better. So most operations on most data structures don't commute, right? But it turns out there are many examples that are still fine and that we would really want to allow, even though the modifications don't directly commute. So here's an example. Our shared value is now list, and instead of assigning or adding integers, what we're doing is appending to the list. Now, obviously, appending to a list doesn't commute with itself. But if we add 6 first, then 7, we get 6, 7. Otherwise, we get 7, 6. So if we just look at commutativity, we would have to reject this. But if we look at what the program actually outputs, it's not the list itself. It's a sorted version, which removes the order from the list again, right? The order information. So this will always return 6, 7, and therefore not leak any information about, whether this add happened first or that one. So we really want to allow this. Here's another similar example. Our shared data structure is a map. We perform puts. So this one puts key 1 and value 6. This one puts key 1 and value 7. Puts on maps also don't commute in general. Because if you have different puts on the same key, which we have here, then the later put will override the value of the first one, right? But again, we really want to allow this because we're not returning the entire map. We're only returning its key set. And that one isn't influenced by the order. So the second key idea here is that we can relax our properties that we're checking and our commutativity requirement in cases where we're only leaking or returning some view of the data, some abstraction of the data. And if this is the case, like in this case, then we can weaken our commutativity requirement to some commutativity modulo and abstraction. So in particular, if we look at the map example, put doesn't commute with respect to the entire map, but it does commute with respect to a view of the map that only considers the key set. Right? It'll be 1 afterwards. The order doesn't matter. Similarly for the list, appending to the list doesn't commute in general, but it does commute with respect to a multi-set view of the contents of the list. That'll be 6, 7, it's unordered. The order doesn't matter. Yeah, so this is how we would verify both of these programs. Our solution from earlier that I sketched doesn't change much at all. The only thing we have to do is, in the beginning, we define some abstraction for our data structure, and we check that initially our value is equal in both executions modulo the abstraction. We check that the actions we have commute modulo abstraction, and then at the end we get to assume something weaker, of course, namely that the final value is low modulo abstraction. So we've built all this into a concurrent separation logic, another one that we call COMCSL. So that's a relational concurrent separation logic because it makes statements about pairs of executions, right? The way I just talked about. Like all CSLs, it allows you to reason thread modularly, supports mutable heaps, and the important point is that it has built-in special support for this information flow reasoning based on abstract commutativity. There's some other stuff in there that I haven't mentioned. So sometimes you have situations where, all the examples that I showed were basically symmetric examples where all the threads were adding values, all the threads were appending to a list. But sometimes you have situations like a producer-consumer thing where one thread only produces, the other one only consumes. And it turns out in these cases you can further relax your requirements, and then you can support even more examples. So this is formalized and proved sound in Isabelle. This was actually really interesting. So the proof is quite different from that of other logics for information flow security because basically our reasoning principle is a different one. So yeah, if you're interested, talk to Thibault, he did that. And we've also implemented it in a prototype verifier. So the reasoning is like that you have to do is simple enough that you can automate it using SMT solvers. So our prototype is based on the Viper verification infrastructure and then ultimately uses Z3. And we're using a product program construction to enable relational reasoning. So basically what users have to do is provide a resource specification that, you probably shouldn't read this, but defines what the actions are that are allowed, defines what the abstraction is, and then beyond that you just write your preconditions, postconditions, loop invariants like in any other kind of SMT-based verification tool. And in this tool, we also support some things like dynamic thread creation, multiple shared resources that go beyond our formalization. So it's kind of, it extends to a broader scenario, not just to like very, very simple examples. Okay. So we've evaluated this on a bunch of examples. So there's, as you might imagine, if your shared value is an integer, then you can do a bunch of stuff that commutes. You can have bitwise operations. You can add things. You can multiply things. I've already talked about lists. So if you have an append-only list, then you can prove that a multiset abstraction will be low in the end. You can do the same for a length abstraction, or if you have a list of integers, for example, for a mean abstraction. What else? I've shown you the example with the map where we have a low key set in the end. We can also, for example, prove that the entire map will be low after concurrent modification if we can prove that different threads insert key value pairs for different key ranges, basically. So they never overlap, they never override each other, because in this case, these different updates commute with each other. And we have some producer-consumer examples that maybe don't obviously fit into this, but it turns out we can actually verify things like this, where we then, if there's only one producer, one consumer, we prove that the final consumed sequence will be low, consumed sequence of elements. And if there's more than one producer, more than one consumer, we can show that now the multiset view of the consumed items will be low, because now the order depends potentially on secret information. Right, that leads me to the conclusion. So we've presented a novel way of modularly reasoning about value sensitivity for concurrent programs. The key feature is kind of that we don't have to reason about timing or secret-dependent timing in any way whatsoever, because this is very, very difficult. And we're doing this by exploiting commutativity, potentially modulo abstraction. We formalized this proof of sound and automated it. There's currently no paper you can read, but I guess we'll put it on archive in a couple of weeks. Maybe it's not really decided, but probably. And for future work, I think this can be extended basically in a bunch of different ways. So we've worked with like concurrency, basically log-based concurrency here, right? But if you have something like a compare and swap, something more fine-grained, I think basically the same principle applies directly. Also, we're doing verification here where we require user annotations, but I think it's almost certainly possible to build a static analysis or something based on these principles. So yeah, I think there's a bunch of stuff one could do. And that's it. Thanks.
Okay, could you go back to the previous slide, 97? Could you comment a bit on the annotation burden, right? How easy will this be for people to use?
Yeah, so that's important. These are lines of code plus annotations. So this is actually, the annotations for these examples it's about 1-to-1. So yeah, 1 line of annotation per line of actual code. Yeah, which is, I guess, it's not really much more or much less than you'd expect for other things. That's like kind of in the normal range, I'd say.
You said you hijack the share-unshare events.
Yeah.
Do you have to use them? Or so, for example, I was thinking of a barrier algorithm with phases, and you know that after each thread arrives at the phase 1 barrier, then maybe you can already prove that you're back good, but you don't want to unshare the variable just yet.
Yes, exactly. So basically, one kind of big limitation of what I've just presented is that you can only ever assume that your shared data is low once you've joined all the threads, right? Because only then you know that all the modifications have been done. But this is something that you could eliminate. For example, if you introduce barriers instead, they would, in principle, allow you to make the same conclusions. And actually, our implementation has like very, very simple and preliminary support for something like this.
Thanks.
Any other questions for Marco? Oh, okay. Good.
Yeah, great talk. Very simple question and also rather technical question. If you have the additional abstraction, is then also the set of operations modulo this abstraction? Because you said the operations themselves are not allowed to depend on high.
So what I meant by that was,
Yeah.
What was this, right? You can't have secret information deciding that you're doing some action one more time here than you do there. The set of allowed actions, so like you can only add or you can only append to the list or something. This is something that you like define once in the proof for every share, and that's not a runtime thing, so it can't really secret depend anyway. That's like a property of the proof. I think you asked something else first, and I forgot what it was.
It was just a single question. My question here would have been, so here I would imagine if you have instead of like ABC on the right side, we just have, I don't know, ABD. But then, like D and C are the same under alpha. Would this then also be fine or not?
So the alpha is defined on these values, right? Not on the arguments. But indeed, so it's for example, for the map. Where's the map? Give me the map. There. It's not actually necessary that you. So this would be fine if you put one H here, if you put the secret as a value in the map. It doesn't have to be the same value in this case in both executions, because the only thing that we're leaking anyway is the key set. So yes, indeed, with the abstraction, we can also basically relax the requirement on the arguments of the operations, and we do that in the logic.
Great, that answers my question.
Thanks. Maybe for the other questions, you can afterward talk to Marco. Yeah. So let's thank Marco again.